Welcome back. In the last few videos, in fact, we looked at Galois extensions. We also defined the notion of normal extensions, and I did a couple of problem sessions in the last two videos where we looked at some properties of normal extensions and also characterized normal extensions, understood how normal extensions behave in a tower of three fields, and I introduced to you an important relation between Galois groups of extensions when you have a tower of three fields. Okay, so today let's introduce a very important notion called separable extensions. Separable extensions are very important, and this in fact gives us a very convenient way of checking if something is Galois or not. So in this video I will introduce to you, maybe you have read these things in a course on field theory, but I need some basic definitions and properties of these, and once we finish this, in the next video we'll get back to Galois extensions. Okay, so in this video it's going to be sort of a review if you have seen separable extensions. If you have not seen separable extensions, this is going to be a very quick introduction to them. Okay, so let us start with an arbitrary field. So let capital F be any field. So I'm going to give you some definitions first. First definition is an irreducible polynomial. So I'm going to shorten it like this. Over the given field is called separable if it has distinct roots. In its splitting field. So remember that this may not have roots in the given field itself, but wherever it has roots, we know that it has a splitting field, so we might as well consider that. It is called separable if it has distinct roots in its splitting field. Just a remark about what distinct means. So distinct means as many roots as its degree. Number of roots of f equals the degree of f. So I'll do a few examples later on, but this is a very common phenomenon. So in fact, most polynomials that you are used to, if you work with characteristic 0, for example, every polynomial has this property. Okay, so it is difficult to find a polynomial which doesn't have this property, but they do exist. So I'm going to come to that after I complete the definitions. I'll give you some examples. Okay, just before I go to the second definition, though we rarely talk about a polynomial being separable, I want to define that for to be able to state the next theorem most conveniently. So a polynomial, I have now omitted the irreducibility condition. So here I take irreducible. Now I am just taking any polynomial is separable if I don't want to say it has distinct roots, because it may have multiple roots, but I want its irreducible factors to be so the polynomial may not be irreducible, but it will factor into irreducible polynomials in fx or all separable. Okay, so the polynomial itself may not have distinct roots, but we want its irreducible factors to be separable. I will give you an example to illustrate this. Now next definition is that a finite extension of fields, of course, always is separable. Actually, let me just first define what it means for an element to be separable. So let K over F be a finite extension. In this course, we are only going to look at finite extensions of fields. An element alpha in K is separable over F. I have defined in one, I have defined the notion of a polynomial being separable. Now I am defining an element being separable. an element is separable over f if its irreducible polynomial over capital F is separable. A finite extension is always algebraic, so this element will have an irreducible polynomial. If that is separable, then the element itself is said to be separable. Finally, a finite extension, this you can now guess, K over F is separable if every element of K is separable over F. Simple exam definition, right? Just like algebraic extensions. If every element is separable, we say the extension is separable. K over F is said to be inseparable. So the antonym is inseparable if it is not separable. That means even one element is not separable. So just like the antonym for algebraic is transcendental, so we say that extension is inseparable if it is not separable. Okay, so now before I discuss some properties, I'll give you just very quickly one or two examples. So for example, if you take is separable, though it doesn't have as many roots as its degree. Here the degree is 2, but it has only one root because its irreducible factors, which is only one actually, is separable. Okay, just to illustrate that, for an irreducible polynomial to be separable, all you need is distinct roots. For an arbitrary polynomial to be separable, you need to look at its irreducible factors. A more interesting example, in fact, every polynomial of Qx is separable, as we will discuss very soon. But a more interesting example is this. So let's take f to be the rational function field over the finite field f2. So this is all ratios of polynomials like this. In the polynomial ring, and of course g must be non-zero. So here t is a variable. So t is a variable. Okay. So in this field, so this is a very big characteristic 2 field, right? So in this field, let's consider, so x will refer now to the variable. So let's take f to be, fx to be x square minus t in f, which remember is f2 t, round bracket t. Okay. So in this polynomial, you take this. So it's easy to see that f is irreducible over capital F. So this is a bit confusing, but if you just pause and think for a minute, it will become clear to you. It is irreducible, right? Because it has degree 2, and as we discussed some time back, any degree 2 polynomial is irreducible if and only if it has no roots. It has degree 2 and it has no roots in capital F, right? That is clear, because what is a root of f in capital F is a rational function. So this such things are called rational functions. So it's like rational numbers, which are ratios of integers. Rational function is a ratio of polynomials. So a root of f is a rational function. Let's say at by bt. I have taken f here, so I should really use some other letters. At by bt in f such that you plug in this equal to x, right? At by bt whole square is equal to t, but there is no such at bt in the polynomial. Okay, so this is something you can check as an exercise, because just consider degree of such an expression. check this as an exercise. If there is such a thing, what you will have is AT square equals BT square times T. So you can't have any polynomial, two polynomials AT, BT which have this property. Okay, so this is not possible. That means AT or BT such that AT or BT whole square equals T does not exist. That means this polynomial here has no roots in capital F. That means it is irreducible in capital FT or capital Fx. But what are the roots of this? Now consider the splitting field. So this is a very crucial example. So it's important for you to understand this. So I'm going to describe this in detail. Consider the splitting field of K of Fx over capital F. So you have capital F, which is Ft round bracket T, and K is a splitting field. And remember, this is not equal to K because F has no roots in F. So this must be degree 2 because you are adding a degree roots of a degree 2 polynomial which is irreducible, and once you add a root, this is something that we know, all the other roots are added, so this is degree 2. What is this field K? And we also remember that every polynomial or every field has a splitting field, so K exists is something that we know. So what are the roots of F in K? See, this is exactly like, so I'll just, though the situation is somewhat unfamiliar to you, this is exactly similar to, this is analogous to adding roots, let's say square root of let's say 2 Q. So what we really do there is Q. You take x square minus 2. Remember, roots of x square minus 2 are square roots of 2, right? So that is a square root of 2. So adjoin this. So here you take the square roots of the polynomial x square minus t and you adjoin root. So it is convenient to denote the roots by root to t, because that's what they are, right? They are square roots of t. So what are the roots of capital F, small f in capital K? Let's denote them by and you would have root 2 and minus root t. This is where, so here for example, roots are, so let me just, roots of x square minus 2 in q root 2 are root 2 and minus root, because root 2 square is 2 and minus root 2 square is 2. So they are the two roots. Remember, a polynomial or a field can have at most as many roots as the degree. So here degree is 2 and there are two roots, 1 and 2. Here also there is degree 2 and there will be at most two roots. But now I claim that there is exactly one root in fact. But since characteristic of K, which is of course characteristic of F, which is characteristic of F2, is 2, we must have root 2 equals minus root t equals minus root t. So in this field, 2 times anything is 0. So 2 times root t is 0 in K. Right? So 2 times root t is 0 in K. That means root t plus root t is 0 in K. That means root t equals minus root t in K. That means root t equals minus root t, and hence Fx has only one root in K. That means it doesn't have, I'm just writing the various equivalent statements, doesn't have distinct roots, because this came up earlier when we talked about some examples of normal extensions. and I hinted to you why they will not be Galois in general. It doesn't have distinct roots, right? Degree is 2, but it has only one root. Okay, so that means it doesn't have distinct roots, or yet another way of saying this is f has a multiple root. So any root that repeats at least twice is called a multiple root. So the conclusion of all this, so all this is to conclude fx, which is x square minus t, which is a polynomial in one variable over the field f2t, is not separable. Okay, it is not separable because it is irreducible and it has only one root. It must have two roots for it to be separable, so it is not. Okay, so as an exercise, and I will come back to this in detail later, but right now I want to move on. So I'll leave this as an exercise at this moment. The extension k over f being this k over f, in this example, that means f is this, k is the splitting field of x square minus t, is normal. This is by definition because it is the splitting field of a polynomial, but not Galois. It is normal, but it is not Galois because if you consider the automorphisms of k over f, I claim that it has only one element, the identity element, right? Because it must send root t to another root of its irreducible polynomial, but there is only one such, namely root t. Minus root t is also equal to root t. So the Galois group has only one element, so 1 equals the cardinality of the Galois group, which is less than the index of the degree of the extension, right? So in fact I have done this exercise, but check the details. If there is anything that's not clear to you, check the details. So you have here an example of a normal but not Galois extension. We'll see soon how to provide the missing ingredient, which is exactly separability. So here the polynomial in question is not separable. Okay, so before we go on to that theorem that I want to prove, which is a crucial theorem about Galois extensions, let me introduce some properties of separable extensions because these are useful anyway to keep in mind. So proposition, so I am going to write this as a proposition. First part is an irreducible polynomial. So f is any field. An irreducible polynomial, small f, is separable. Okay, so if and only if the greatest common factor of f and f prime, which is the derivative of f, is 1. So we write this as the GCD, so is usually denoted by f comma f prime in brackets. So f prime is the derivative of f, the formal derivative of a polynomial in one variable. You know how to do that. Okay, so that is the first part of the proposition. It's a good way to check if something is separable or not. You simply look at its derivative and compute the GCD. And this GCD, the point is this GCD, so this GCD can be computed in f itself. Okay, so this I will explain again in the proof, but you don't need to compute, you don't need to see if they factor, and if you know that they factor completely, then you can easily look at the common factors and see the GCD, but you can actually do that in f itself. Okay, so now the second part of the proposition, which is actually useful for us, is if characteristic of f is 0 or if f is a finite field, then every polynomial in fx is separable. So separability is no condition at all if you have a characteristic 0 field or a finite field. And the third statement is an immediate consequence of 2, but I want to write this because it's useful to keep this in mind. Let f be a field of characteristic 0 or a finite field. So f is either characteristic 0 field or it's a finite field. Then any finite extension of f is separable. So separability is no condition at all again if you have a field of characteristic 0 or a finite field. Okay. So 3 of course follows from 2, so I am going to prove 1 and 2. So let me quickly prove this. As I said, my goal here is not to do this in a comprehensive manner, but give you a quick idea of how to prove this. So again, this is something that you would have seen in any course on field theory. So just to prove one, the crucial idea is the following. Suppose A in F. So the point is, this is a general point, so which I will write first. Okay, so we have f and f prime are in the polynomial ring over capital F. Suppose K is a finite extension of f where both f and f prime split completely. For example, you can take K to be splitting field of f times f prime. Okay, so f and f prime are both going to factor completely into linear polynomials in K. Then GCD, okay, so I'll just write this as f comma f prime is 1, which is the terminology that I'm following here. So if the greatest common factor is 1 means GCD is 1 in bracket f comma f prime in bracket is 1 if and only if f and f prime have no common roots in K. Okay, so they may not have roots in f, but they will have roots in K for some arbitrary, some particular extension K, and if they have no common roots there, they have to be irreducible, they have to be co-prime. So this is really called co-prime. We say f and f prime are co-prime. That's the terminology. So this is some general ring theory statement. Okay, so this is from some general results about division of polynomials for extensions of rings fx contained in kx. Okay, so I don't want to spend time on this. Okay, this is a general statement, so I might as well work with the splitting field of f times f prime and see if they have a common root. Okay, so I will really study this. So suppose A in K is a root of, let me start with a root of f. So that means, that gives, so here I am really working in capital Kx. That gives f x equals x minus a times gx, right? This is the meaning of a being a root. That means x minus a divides fx. differentiating both sides, we get f prime x is equal to the product rule you take. Formal derivation of polynomials follows the usual derivative rules, right? So this is x minus a times the derivative of g plus gx times the derivative of x minus a, which is 1. So this is the important equation that I want to analyze. So now I claim that a in k is a multiple root of f. What is the meaning of multiple root? So that means x minus a square divides f, right? Because you must have a root appear at least twice in its factorization in a splitting field. So this means x minus a whole square divides f, but this means x minus a divides g, because x minus a is one factor like this, so g must also have a factor of x minus a. And I claim that this is if and only if, these two are just definitions, but this, the last statement is the consequence of this equation, because x minus a divides g, that means x minus a divides the right hand side here, so it divides f prime. On the other hand, if x minus a divides f prime, that means x minus a divides f this as well as, of course, it divides this, so it divides gx. So this implication follows from star, right? But if x minus a divides f prime, that's clearly same as a is a root of f prime. Okay, so a is a root of f prime. So now this is the statement. So a is a multiple root of f if and only if a is a root of f prime. So that means, okay, so okay, now let me just write down a series of things. F is separable. F is separable if and only if f doesn't have multiple roots in K. This is the definition. It doesn't have roots, multiple roots in a splitting field, but of course it doesn't have multiple roots in any field where it has roots, right? It need not be splitting field, because its roots are what its roots are. So whether it's splitting field or some extension of splitting field, you get the same statement. So it doesn't have multiple roots in K. That means f and f prime have no common roots right, because a is a multiple root of f means a is a root of f prime. Now if nothing is a multiple root of f, then it cannot be a root of a. Every root of a, f is not a multiple root of f. That means that root is not a root of f prime. That means f and f prime have no common roots in K. This implies f and f prime are co-prime in fx itself. Okay, this, as I said, is a general ring theory statement. That I started this proof with. So this is something that you can look up somewhere else. This is just a simple fact that you can find, for example, in Artin's book, Michael Artin's book. So if they have no common roots in K, in the base field itself they cannot have a non-constant common factor. So that means they're co-prime. Okay, so this exactly means, so hence, okay, so I think 1 is proved, right? So 1 is proved. Okay, so let me stop this video here because it's already been time. I will stop this and continue with the proof of the remaining two parts in the next video. Thank you.